Hello, everyone. Welcome to another episode of Robo Papers. Super glad today to have Ge Yan with us. He's one of the co-authors of this paper called ManiFlow, a general robot manipulation policy via consistency flow training. Thank you so much for making the time, Ge Yan. Maybe as a start, if you can share a little bit about yourself.
And thank you for having me. My name is Ge Yan, and I'm a second-year PhD student at the University of Washington, advised by Professor Dave Fox. Previously, I did my master with Professor Shalom Wang at the UC San Diego. So this project is also in collaboration with both UC San Diego and the University of Washington. Yeah, I can start. So recently, we've seen that the great progress of these large-scale robot foundation models like Pi0 can do very open world manipulation. And there's a model called IBM 1.0 by TOI. It can do very dexterous and long horizon tasks. And despite that, we've seen that a lot of progress in these large-scale VRM models, we can see some limitations. So here is one example that what we saw in IBM 1.0 paper. So this figure shows the performance of IBM model in simulation tasks. So the upper side, the figure shows the in-distribution performance. And when we add some distribution shift to this simulation task, we can observe some performance drop on the distribution shift in most tasks. And also for Pi0, and here we show the results that evaluated by Grosvenor Lab at the University of Pennsylvania. So the left video is the task pour water from teapot into bowl. So we can see that Pi0 fails to manipulate a novel glass teapot with 0% success rate. And the right video shows the task pick the black box on the white box. So, and this task that they have a new background and this t-shirt, and they cannot handle this unseen background. And if we see the limitations of these large-scale foundation models, we would ask a question that can it be really applied to real world? It's like, so for a human that we usually need to deal with some messy kitchen scene with cluttered objects. And the question beside of these things like first is generalization. So we always deal with these unseen objects, containers, or this food, and being able to generalize to different objects is very important in this scenario. Also, we can observe that how to have a very comprehensive understanding of this spatial relationship between these different objects, there may be some occlusions, is also very important. And can we just achieve maybe over 90% success rate by just collecting more robot data in such scenarios? And there are two problems. So first is the data efficiency, that we cannot assume that our trained data can cover all the scenarios in real world, that considering we have so many diverse kitchen scenes as objects. And if to train a robot policy that can really generalize to all these scenarios, that we cannot assume that we can collect maybe hundreds of thousands of demonstrations for each scenario. And also there can exist some real-to-real gap. So right now, the most open source datasets that are mainly collected in some fixed kitchen scene or laboratory or the factory scenes. So that is still very limited and compared to a very diverse real-world scenario. So in this project, we are more focused on modeling perspective, that how can we have a better architecture that allows us to train on much less data, but still have equal or even better performance, and which can make our system more practical. Yeah. So we can first take a look at the performance of ManiFlow. So here shows two videos of ManiFlow. Like the left is ManiFlow doing a long horizon stack cup scene, and it requires some precision and spatial reasoning. And the right is like that we train the ManiFlow in a egocentric equine humanoid robot, and it can generalize to some unseen objects and also the different background colors. And one thing to note is we only use 30 or 50 demonstrations for each task to achieve some reasonable performance. And in comparison, that IBM used 200 or 500 demos for a similar task difficulty. So what is ManiFlow policy? Here is an overview of the pipeline. So basically, a ManiFlow takes either 2D or 3D representation with a visual encoder And we propose a expressive DITX transformer to handle all this different modality data. And finally, we use as a consistency flow training. That's a joint optimization between flow matching and a thing called consistent training to generate a high dimensional action sequence. So first thing is about the egocentric 3D representation. And I really enjoyed working on this humanoid robot, especially with eccentric representations, since I found there can be many benefits behind it. So one thing we observe is 2D is really vulnerable to light change and scene distractors and the novel objects or backgrounds, while 3D is usually more efficient and generalizable. That means it can take much less data to achieve similar or high performance, and despite it relies on high quality depths. But recently, we've seen some progress in foundation stereo or depth estimation model that make me more optimistic that we can use some AI models to estimate those very high quality depths and without needing very expensive sensors. And we can also see that this kind of eccentric representations is really robust to viewpoint change. So in the training data, you may have your camera and the movement, but your model is actually learning those dynamics during the training. And that allows that the model, even though in the test time the camera may change a little bit, or you can have different angle, but you can still generalize well.
So just a couple questions. Sorry. So you have so you're on the previous slide. You were just talking about how your model can take in 2D or 3D. Right now, right. So right now you're going over the advantages of egocentric 3D. So can you tell us a little bit about? Are you mostly what is it? What are you actually doing then? Are you training on both? Are you training on 3D? What's the?
Oh yeah. So previous slides it can take 2D and 3D. It's mainly in simulation that the model because the DITX can take either 2D or 3D, and we have the ablation in the later experiments. Right now, in this real-world experiments, we are mainly using, especially in this setup, we are using egocentric 3D, and that's the result here.
Okay, so yeah, using egocentric 3D here. Great. And so because of all these advantages, and you are assuming you've got this nice sensor like Intel RealSense, something with high quality depth still, but the idea is that in the future, maybe you could move to something like foundation stereo. Is that right?
Yeah. And actually here is a Z camera with
use a Z. Okay.
Yeah, it's calculated stereo. Yeah, and the final thing I want to bring up is eccentric human data plus 3D. So previously, one of my lab mates, Roger, I think he shares his paper on humanoid policy roughly equals human policy, something like that. But it shows eccentric human data can be very helpful and more scalable and still helps the model to generalize. And I think a few direction about how to leverage those eccentric human data with 3D representation will be a very interesting direction. And the second part is about the diffusion transformer architecture. So here is again the example of LBM model. So LBM is actually the architecture is quite simple. So it uses an architecture called a DIT block. So that is first proposed in image generation, and then people apply it to robotics, and basically just equip it with a diffusion policy and scale it up. And what we see LBM paper is compared to the vanilla transformer block or diffusion unit in original diffusion policy paper, a DIT block is actually much more efficient, considering those generating those very high dexterous robot behaviors. And there have been some evolution starting from DIT to many other DIT family architectures. Here I mainly show the DIT-X, which is in our paper. And so we can first take a look at the left, which is DIT. The key idea between all these DIT series architecture is something called area 0 normalization. So it's basically some adaptive layer norm for modulating those observation signal. So basically in this architecture, you can have this time step T, and you can have some observation embedding or language embedding as a conditioning. And then you predict all this scaling and shifting parameters like this alpha, gamma, and beta to normalize the different layers of your transformer block. And that is very important since it allows more adaptive control over your different input signals. One thing about the DIT architecture is especially when you deal with multiple modality like LBM did, It basically, for example, you have visual observation, you have language observation, and you just mix all these modality equally and compress them into embeddings for a global
Did we lose this
condition.
internet? I think you froze.
Yeah.
Okay.
It's-
Okay, yeah. I think you froze for just a second.
Can you hear me right now? Does it work?
Yeah.
Okay. So I can continue.
Yes.
Yeah. You're saying basically you can, this allows you to mix, like basically you mix all the modality equally.
Oh yeah.
Compression.
Yeah. Okay, I can start from here. And this design actually cannot handle this multimodality conditioning efficiently, since when you mix every observation embedding together, it's very hard for the model to distinguish between different. And what we did here is like we try to disentangle those low dimensional and high dimensional signals. So for the time step t that with a low dimensional but maybe high frequency, so we use at the area 0 a conditioner for this low dimensional signal to produce some global conditioning. And for those high dimensional signals that are visual or language tokens, that you may want to have a very fine-grained understanding of your language instruction or this visual localization. So we use cross-annotation layers to interact these high dimensional tokens with action tokens. So this is what we call some context conditioning.
Sorry,
So-
Ge, I have a quick question. Sorry.
Yeah.
Could you say again, like I'm trying to understand low dimension and high dimensional signal. Could you give some concrete example? You're saying something like, for example, if it's the depth data, like where would that go? Is that considered high dimension?
So this low dimension, one example is time step t, so it's a one dimension. It's just a scalar. So, or you can consider other very low dimensional robot states. And high dimensional is more about like, for example, your image, you may have maybe hundreds of these patches, and you convert your tokens, and each token have so that we consider here is as high dimensional input.
So so basically in the previous one in DIT, before you have everything, all of your images get compressed down to a single embedding, which is obviously going to mean that you can't cross-attend to particular features in the image depending on what the action is, which is why you add this middle section here with the adaptive cross-attention. Okay.
Yes.
Okay.
Yeah, and another thing to note is like we add this cross attention layers like to normalize like different modality, right? Image or language they actually have different structure and a statistic distribution. So you want to add different normalization to different modality, and that's a very important principle in designing this architecture. And this design actually allows more fine-grained adaptive control for this multimodality conditioning.
So I can see how this would help. But does this end up making the network like a lot bigger, or why does this decrease the data requirement, I guess?
Oh yeah. It's actually, I would say that yeah, it indeed makes the architecture larger, but not but when we consider the performance boost that we have, I think is still worth it, because actually this is the intermediate here, the cross attention layer is just within each layer is just I would say that the parameter when you calculate those parameter, I would say it's basically equal like this set of attention layers, and that design actually allows you to more efficiently to comprehend your data with different modality. That design actually, that's why I say that it makes your model more efficient to leverage those data, right? Because with the same amount of data with our previous DIT architecture, you may find it difficult that to fully leverage all this different modality information.
Understand. So even if it ends up increasing your parameter count by a third or whatever, or half, whatever it is, I don't know exactly. But even if it ends up massively increasing your parameter count, you're saying that doesn't mean that we need more data to train this much larger model, because it's just so much better, because it's more efficient, because it doesn't have to pass all this image information through a single embedding. Is that right? Okay,
Yes.
cool. Awesome.
Yeah, and the right is a figure shows the performance in the training. So first we can see that this figure shows the multitask training performance. So the upper side shows the MSE arrow that DITX actually shows faster convergence compared to without this adding this cross attention layer normalization. So that also partly answers your previous question, that it actually makes the training faster. So it's more efficient. And also as the training goes on, we can see the performance also increases much faster than without this cross attention at zero conditioning. And yeah, we further did experiments on meta-word language conditioning and multitask learning. And so we can see the DITX, which is this orange curve. DIT is this green curve. And of course, the middle one is called MDTI. I didn't elaborate here. So basically, we can observe that across all 10 tasks, that in most tasks, DITX shows both faster convergence and also higher eventual performance.
So by multimodality, can you explain what you mean by that?
Oh yeah, here the multimodality input means the point cloud and the language here, and also the actions.
Sorry, could you just describe a little bit what are these meta world? Is it a benchmark in simulation?
Yeah, this meta world is a simulation benchmark.
And these are language. So the instructions are given in language.
Yeah. So this setup is basically for each task we have a language instruction, and we do multitask training.
Got it. Okay.
Okay. So we can finally go to the generative modeling part. So recently we can see that from 2024, like we see diffusion policy and recently the flow matching policy. We can see here is a visualization shows. So this visualization shows the flow matching and the diffusion model. Like the left part is like the initial condition and shows how this model gradually denoise into your target distribution. So we've seen that flow matching and diffusion model has been pretty successful in robotics, and many VRA models has been using this flow matching and diffusion models for its action head. And we observed that flow matching usually generates smoother trajectories, so it has less accumulation error, and it has usually brings better performance. And here I briefly introduce what is flow matching. And here, this slide is taken from Kai-Mi He from his talk called Towards End-to-End Generative Modeling, which is a great talk that offers a lot of insights into flow matching. Okay, so, we can use, in this figure, we use X to denote that this black point, which is a data distribution. This red point is we use notion epsilon to denote this noise. And we can randomly sample this intermediate location. We call it ZT, and by doing linear interpolation between the noise and the data, we can get the ZT is 1 minus t multiplied x plus t multiplied epsilon. And by taking the time derivative, we can get a conditional velocity Vt with epsilon minus x. So that's how we calculate this conditional velocity. And what actually the flow matching learning is actually the expectation of this all conditional velocity. Because in any point in this, especially in the early train stage, we can observe that this ZT can have multiple conditional velocity. So the model is actually learning an expectation over all this conditional velocity, and we call it as a marginal velocity, which is a modularization over all this potential conditional velocity. So the right figure is actually shows that what the model is trying to learn. And we observe that there exists some long straight marginal paths. So you can see that is a curve. And this kind of non-straight path, that means the harder integration when you do the inference. And it requires you to do need more inference steps. And so the motivation behind our consistent flow training is more like, how can we straighten this probability path in flow matching so that the model can generate those actions with fewer inference steps and with higher quality. So we propose consistency flow training, and we can take a look at what flow matching is trying to predict. So given like a probability.
Sorry, before we move on, could you go through explain maybe a little bit more what the intuition is behind why these paths are curving in the first place? I assume it's because like it's moving towards the center of the distribution. What's going on here?
Yeah. So you mean why?
And these are velocities, just for anyone else who's like listening, right? So these are velocities, not in like, these aren't robot trajectory velocities. These are velocities in like trajectory space. They're like where your estimates are, right? So what's going on here?
Oh yeah. So basically, like here, why the curve is because in early train stage that we can see that given this, we can see a lot of intersections between different the data points and the noise points. So you can see for robotics, this data is actually your action, right? So you can see that there are many intersections. So that can give you multiple velocity prediction. So that's the model is trying to comprehend that when you have many points and many noise points, the model is trying to estimate that the expectations over all possible condition of velocity, and then use that we can get the right figure.
So okay, so the reason that there's a curve though, it is because like some of these points are kind of far off to the edges of the distribution, and they're kind of could be we basically just don't know which. Okay.
Yeah, actually you can understand in that way that this is more like a first training round. Like we've seen some work that use some distillation, right? So basically there is a work called a reflow. So basically in the initial training round, we can see that ideally that we want all this possibility paths to be as straight as possible. But when you don't have enough data, and actually when you do the optimization, we will see that is actually not straight enough. But so some work uses some distillation that it tries to gradually straighten this path in the second round when you have a teacher model to gradually straighten the path. So that's more like optimization process. Okay. So flow matching is actually, you can see in this path that it's trying to predict those instantaneous velocity that defines the tangent direction of this probability path. So initially it's a curve, and there is no constraint on this prediction that whether this velocity should be consistent or not. So here we add something called a consistent training. So we can have like multiple intermediate points, and we hope that by giving all these intermediate points, we can approximate the same target data point. And that meaning that all these points can eventually reach to this same target data point. And in this way, we want to enforce the self-consistency within this probability path. And during training, we will jointly optimize both flow matching and consistent training to ensure the model can both predict the instantaneous velocity and also ensure the self-consistency. And here is like in more detail that with the robot data. So we have this noise actions, which is t equals 0. And we have t equals 1 that we have this clean target actions. So we have this noise data pair. And I use this orange line to represent the flow of the path. And conceptually that we want to sample like multiple intermediate points. So from these red points, xt to xt1 and xt2 with continuous step size 30 and 30 prime. And we can get all this velocity prediction of pointing from xt to xt1, xt1 to xt2. And one thing to note here, instead of like previous like diffusion flow matching model, you just take xt and t, but we add an addition term 30, which is but basically following a paper called shortcut model that is 30 to basically inform your model that how large your step size your model want to take, and that can allow the model to be more informative of future velocity prediction. And given all these sampled intermediate data points, and we want to infer the flow consistency across these red points. So that, and this red point corresponds to previous slides that we can have those sampled intermediate data points, and we want them to reach to the same target data points. And in order to do that, basically here I use a blue point, which is xt2. So I use this to show the process. So basically we use this xt2, and given this velocity prediction, we can approximate its tilt. So that's approximation of this target data point. And we hope it to be as close as to the ground truth target data point. And we use this estimation to backtrack the velocity at the first point, which is the time t from xt, and we can get the velocity from xt to the final target data point. So basically we get this new velocity, and we try to do the MSE loss so that we can say that from this blue flow curve, from this blue point, we can get this velocity that matches that the velocity that is originally predicted by this first data point. And in this way, we gradually make this flow trajectory more and more consistent. Yeah.
Gayan, I have a
okay, go ahead.
sorry, I have a question. Will this work well still? I mean, this consistency flow training, if you have really long horizon task, if your time is very, very long, what do you think? Or how do you think about that?
Yeah. So I would say that the time, do you mean the horizon, right? So so the time here, time equals 0, time equals 1, they are actually not the horizon. They're not meaning the horizon. They're just the scalar that you input the time. So this time step is different from the time step in the action horizon, right? So for this consistency, I tried a task like the previous I showed, that the stack copying, and I found that with a longer action horizon, actually the model performs even better. So I try, like, for a long horizon task, we try to set the action prediction horizon to be 16, 32, and 64. And we found that actually 64 performs the best. So in that case, I would say that this consistency actually is not harmful to those long horizon tasks.
So I think this is one of the things that's most confusing to people who are first learning about this kind of stuff, right?
Yeah.
Is that there's like two different
That's it.
definitions of time and velocity, because there's the time that it's spending optimizing at test time, but what it's learning to do is how these trajectory points move, which is like what's happening here, and then there's also the time and velocity along that final trajectory, which is always kind of
Yeah, I agree.
That always gets me.
Yeah, these actually are two different concepts, right?
Right. Yeah. And they both use the same terms for everything, which is, of course, extremely confusing if you're first starting to try to learn about it, in my opinion. But also, okay, sorry, Michael, wait, did you have anything else? Because there was...
No. Yeah.
Because I'm also, I still kind of don't, and I'm sorry for the dumb question here, but I don't quite understand why this large consistency term would help. Because, okay, so you have the random term, and you're predicting this loss, as far as I can tell, is going to be just telling it to go to the final position in the trajectory. So that's essentially the same as before we started doing things like diffusion and flow policies and just predicting the end goal, right? So why does this help? Why are we doing this then? Or rather, I assume that it is the combination of this with the traditional flow loss that actually makes it work. So how do you balance those two things? Maybe that's the more intelligent version of the question. Does that make sense?
Yeah, I think it's a great question. I think the thing really help we can view this consistency as a regularization term. Basically, previously, for flow matching, as is shown in this figure, is basically predicting this instantaneous velocity, right? So actually, as the training goes on, we do see that this probability path can be straighter and straighter, but it's still not good enough. That's why, like, we found out when you added this consistency, it can make this path straight much faster. So I would say that if you are training long enough and you have enough data, I would say that the gap between flow matching versus without consistent training, I would say it will not be not large. So I think they will gradually converge to the same performance. But the reality is we usually don't have enough data, right? We don't have that much data, and we cannot train a very long time. And in that case, we found that a consistency can help the model converge much faster, and also allows the model to use less denoising step. So that's the advantage of adding this consistency.
Do you think there are particular classes of problems where this would hurt, like maybe like shaking a drink or something like that, where it's again hard to visualize because this is these different. Yeah.
Do you mean whether this consistent term can harm those very dexterous behavior?
Yeah, basically. Yeah.
I haven't found that yet, because what I observed. So here's the interesting thing. So maybe I can show the video here. So actually, in this we did a lot of tasks that in this bimanual setup, that what we observed that with flow matching or diffusion policy, the model actually usually cannot handle it very well. We can see a lot of inaccuracy. We can see that when it comes with, for example, with this cup stacking task, that it cannot actually place these curves very, very precisely. I didn't observe that adding this term can somehow like make things that work in diffusion or flow matching policy that doesn't work with consistent term. So yeah, I would say that we haven't observed that yet.
So how about how sensitive is it? 'Cause so you have these two different loss terms. I assume you need to balance between them. Can you talk a little bit about that?
Oh yeah. So since we have two loss terms, we are actually we will actually do that in your mini batch. So for example, we have a batch size of 64, and a third force is like on flow matching training. So 75% is like you have this instantaneous velocity loss, and the rest 25% is on the consistent term. Because when we view this,
Oh, that's interesting.
yeah,
Yeah.
actually it's much easier to optimize this term, right? Because the instantaneous velocity is rather easy to predict. But this consistent term is like, it can cause a lot of variance. So when you try to regularize your model to predict the very consistent velocity, that can make model very training very unstable, right? So we use we use a smaller batch size for consistent training and uses a larger batch size for flow match.
So you're training them both at once, but with separate samples. Why not just train them? Why not like, I don't know, put like a quarter of the weight on consistency training and train with the same example on both? What stops you from doing that?
Yeah, I actually also tried that. So
Okay.
why we use a mini batch is because to save computational cost. So you can also do this for all the samples, you do the flow matching and then you do the consistent training again. So that's 2 times the computational cost, right? So we found out that we don't have to do them at the same time, but this performance is still very close. So we can reduce a lot of computational cost. Okay. So eventually we come to the experiment part that in simulation, we did a very systematic evaluation on like 64 tasks from 4 benchmarks. So it covers like single arm by manual and also from gripper to multi-finger hand. So the main focus is really for dexterous manipulation. And we can first observe some consistent performance improvement. So we have both a 2D ManiFlow policy and a 3D ManiFlow policy. The difference is like the 2D takes images and 3D takes point cloud. And especially I think in this robot twin benchmark is a bimanual dexterous manipulation benchmark. We can see the gap is quite large compared to a diffusion of flow matching baseline. And we also did multitask training with 3D diffusion, flow matching, and ManiFlow policy in MetaWorld. And this covers 48 tasks with a language condition. And we can see that in different task difficulty and eventually the average performance, the gap is also very obvious. And another thing is the few step inference, because the motivation behind the consistent training is like we want the model to generate a very we can say that straighter possibility path, so that the model can actually, when you do the integration, you can use much less inference steps. So we compare ManiFlow with all this from 1 to 10 different inference steps, and we can see that with 2 steps you achieve the better performance. I think with 1 step is the second best, and the rest is very close. But they're all better than diffusion of the matching policy with 10 inference steps. And here's is a task visualization of task push T, basically comparing ManiFlow with diffusion policy, that it can achieve 10 times faster inference. And eventually we compare ManiFlow with large-scale Pi0 model. So here we want to test the learning efficiency and the generalizability. So the benchmark we use is the Robot Twin 2.0 on the right. So during the evaluation, the model can experiment all this domain randomization, including those clutter scenes, its destructors, light change, and also the table head. So it's very challenging for this policy to be tested. And we try on 4 tasks, and we found out that out of 3 or out of 4 tasks that ManiFlow shows a better performance, I think, and we only use 50 demos. I think it really shows the efficiency of one part is about 3D. So 3D is usually very good in simulation. Also, I think 3D can usually helps the model to generalize to all these distractors much better than 2D models. And
sorry, Ke-Yan, I have a question. Did you have any intuition like why particularly for lift pod, like the delta is so large, and then for something like open laptop, it's kind of similar? Do you have any thought about that?
Yeah, I think, I didn't show the fader videos here. So the fader mode of Pi0 on this task, on different path task, is when you did grasping, it can miss this handle a little bit. So this different part task is actually requires a better geometry understanding. Like you can see that even though a tiny miss can cause the fader, but for this open laptop task, it's actually much easier, right? You just need to grasp and you just rotate it. So it doesn't include some very precise movement here. So I think the two tasks are actually represent different difficulty, and we try to scale it up that from like in this figure from 10 demonstrations to eventually 500 demonstrations. So what we want to see in this experiments is like can ManiFlow it shows better performance than Pi0 in both low data regime and the eventual fine scaling to 500 demos. I think for a lift pod task, we can see that 50 demos, and I think the gap is the largest. We can see ManiFlow is 64 and Pi0 24. But we can see that as you have more demonstrations, Pi0 also gradually increases to 94% success rate. So that shows the data efficiency of 3D ManiFlow is much better. But for 2D policies, as long as you have enough data, the gap between 2D Pi0 model with ManiFlow can be smaller. And for real world, we test on like 3 different real world embodiments, putting like Bounding Vision Pro is a bimanual setup with this human haptical feedback for data collection, and also the humanoid open television teleoperating system, and also the droid setup. So, and I think the challenge mainly lies in this humanoid setup, that since it has the largest degree of freedom and it also has those active eccentric sensing, that makes the model harder to learn. And here we show the robot performance. We mainly compare with DB3, which also takes those egocentric point count as input, and we observed that 98% success rate improvement on all 8 tasks. And we also do the robustness test against or different perturbations like different objects, backgrounds, and also human can add some distractors, and also all these different perturbations in your inference time. Yeah. So I think the key takeaways for ManiFlow is like some simple yet effective architecture change. It matters a lot. So because recently I think people are all discussing the data, right? So with enough data, we believe that these VRA models can scale really well. But I would say that it's not only about data. There are many problems into the perception side, into the architecture, that how you make your system more practical, and you need to consider that when you don't have enough data, that how your model can handle that scenario. So we think some design in the diffusion transformer, especially how you handle those multiple data input, even your vision encoder, and some normalization layers, that can be vital to your policy performance. And sometimes that it can bring even larger impact compared to adding more data. And the second thing is about especially learning those multiple data with imbalance. This question comes to like when you have those language conditioning. And one problem we observe with VRA model is like the language following capability is still not good enough. So that's partly because we have far less language data than those visual data. So how do we efficiently learn from those data with this kind of imbalance? Also, this can also happen in tactile data. And I think in the architecture side, we need to fix this problem too. And second thing is about full matching plus consistency is efficient, and it's all about like how we make this generative modeling that is more is more efficient is in terms of like when you have those noise and the data samples, how you generate those straighter passes and without losing a very significant property of these general models. And we also kind of wondering that is there a better formulation for this general modeling? And the third thing is about that egocentric 3D representation really matters. And the benefits of this 3D data is like you actually require less data, but you can actually perform better than the 2D models. And the recent progress, especially in the VR glasses, that allows people like to scale those human data, and also we can use those depth estimation model to equip it with those 3D information. And this combined can provide a very scalable pathway towards egocentric 3D representation policies. Yeah, I think that's all I want to share today.
Yeah, I have a question about, this part about when you say efficiently learn from multimodality data. You say something about like typically a lot of this data, like for example, is very, let's say, constrained on the language side. How much do you think, like, what is the limit? Like, how much can you push this now that you have this, flow matching with consistency? Like what you propose in this paper?
Yeah, I think this paper, this data imbalance, as you referred to the language constraint.
I mean, like you say, it could be language, it could be other things. It could be like, let's say, tactile, which is also very, maybe probably less than language even.
Yes, I would say that it's mainly about the architecture side. So the DITX architecture here is like allows you to how to process this different modality more efficiently. But that still comes to the problem that even though that given this kind of data you can still leverage very well. But if you want to do some very open world text manipulation, like with open world language understanding, or as you said, with tactile data, that whether you can, even though you only have very few tactile data, can generalize out of the box, I would say that's still very difficult. And I would say that that's more like a combination effort between the architectural advancement and also the data problem. So I don't think that the improvement on a single dimension, like either data or either architecture, can solve that entirely.
Yeah, I guess since we're about wrapping up it, like what we usually ask is also like, imagine if you have like a couple more months left, on to work on this paper, like what would you have like squeezing more into this paper?
Yeah, I think I would be really interested in like how to scale it up with more 3D data. So I think that's the question behind this paper, is because I've seen that the efficiency between this new architecture and this new generative model formulation, and we've tested on that many real world experiments, but I still encounter problems like, as you said, either language and following or those spatial generalization. That when we have those more 3D data, which is actually what I'm doing right now, this is especially with more eccentric 3D data, can it generalize much better than current version? I think that's the thing we need to push forward with.
So when you say more data, do you mean like more like just demonstration?
Yeah.
Per task? I see. Because you only did one time with the 500 for the pod lifting the pod, right? Everything else you did 50.
Yes.
Yeah, but I guess, okay, so what you're saying, more demo per task, but then your expectation is that it will generalize actually still eventually to different scenes and different objects.
Yeah, right now I think even though with like many cases like maybe in real world tasks like with 3D demos, it's like pouring water this task. So even though with 3D demos, like 3D ManiFlow can generalize to a different type of bottles and it can do pretty well. But what I want to do is like, okay, can you dramatically change your environment, right? With all these kind of different background textures and this with a lot of these structures, and right now it still struggles with that. And I believe with like more diverse data, like maybe 100 demonstration per scenarios, and if you can have like 10 scenarios, I would say that can already generate very well in many tasks.
Yeah. Are there any like papers that you come across recently that you like kind of blew your mind, or you want to give a shout out to?
Yeah, I would say the main progress I'm tracking recently is more about reinforcement learning, right? Because I would say that There have been a lot of RL papers, especially real-world RL, that claim that you can actually make your imitation learning policy that can reach nearly 100% success rate, right? And I think they all sound very exciting. But I would say the problem I'm looking at is more about like how can we have a good reward model that, because we don't want to those handwriting reward design for each task, right? Can we have a very general reward modeling? And we also need to consider that when you do the RL post training, something like that, we don't have enough failure data. So right now we have all this data is successful data, right? This demonstration data, but we don't have enough failure data for RL post training. So I think RL is generally a very promising direction in the next, but there could be many problems behind it, and I think how to fix them would be very exciting.
Are there any specific papers that you thought were cool lately?
Yeah, I think a recent one by Kun Lei and by Tsinghua University, I think is very good. I think it's just today or yesterday.
What's it called? What's that paper called?
Yeah, I saw this one, I think.
Yeah, I think it's RL 100, right? Yeah, it's called RL 100.
Yeah, that one.
RL.
Yeah, do you want to say it?
100% on like 900 tasks, 900 examples or something like this. 100% success rate. Yeah.
Wow, that sounds crazy. Okay, cool. I need to read that one. Awesome. Yeah, okay, cool. Well, thank you so much for making the time, Ge Yan. Really cool what you've done here.
Yeah, it was a really interesting discussion. A lot of cool details. Very, very educational, very informative. So thank you for talking through it with us.
Chris, what have you learned?
So quite a lot. This was a pretty technical one with lots of discussion about like architecture changes and how to handle cross attention for conditioning your flow policy and different losses for flow policies. So there's a lot of detail. I think the broader takeaway, like we were talking in the end, I really liked that there's people thinking about like the stuff like losses and architecture tweaks and so on for these, because like a lot of the time in these, even in these that we have the people talking about scaling data, and like there's a real possibility that at some point those will cap out because we can't get past some threshold. So it's great to see people doing this kind of iteration. I don't know. What about you? What do you think?
Yeah. Well, definitely quite technical, this one. I try my best to follow along. Yeah, actually, can you educate me again? Like, I'm still a little bit confused about the tool time definition, you know?
Yeah.
So there was the normal time as humans understood it. The other time, what is the other time that he was referring to when he showed that? There's
like the time, like as I'm like moving through space, like following the trajectory that my hand follows, right?
Yeah.
But there's a second one, which is like, but what a modern imitation learning policy does, right, is it doesn't predict like an action. It predicts like a trajectory. So it has all these different trajectory points, right? Like say they're where my fingers are. And what happens is that in flow policy, it's predicting this velocity to line these up into the trajectory path that I'm actually going to follow, right? So that's the velocity that he's talking about. It's how fast this point is moving. So this point may be 0.3 in the trajectory, and it may be happening at t equals 0.03 or something like that. But like the velocity that he cares about is the velocity that is moving through trajectory space to get into the position that it will be at for when you actually execute it. And then, so this runs faster than real time at some. Does that make sense?
Yeah, I think so. Like it's a little bit like maybe planning ahead, like a few steps ahead to.
Yeah, it's like so.
It's like the action chunking.
Yeah, so this is an action chunk. So the flow policy is operating on an action chunk. It's operating on like a little trajectory snippet that's like, I don't know how long his is, but like half a second long or a second or 2 seconds long or something like this. Yeah. Right. So what he's saying is that there's a point. So like for the velocity one of those points is a point in a trajectory. So like, let's say it's the position and velocity the robot will be at 0.7 seconds, something like that. So that's a point. And then, so that gets initialized to something. So maybe it's initialized randomly, right? And then I have that point in space, in trajectory space. So this is like, again, where will the robot be and how fast will it be moving at 0.7 seconds into this hypothetical trajectory that I have not executed yet. And then the flow policy is going to, for some amount of time, it's going to take that point and move it, right? And it's going to move it until like, I think he was saying 64 steps, but like it's going to move it until it's going to do it that many times. And then it'll be, after it's done that, it will have moved So the point where the robot will be at 0.7 seconds has moved until it's in hopefully the final projection. So now if I do this, it's like correct. And if I move my arm along that trajectory at 0.7 seconds, it'll be in the correct position to do whatever my task was. So yeah, I think it is good to think of it as it is, you could kind of think of it, it's learning to optimize the trajectory that the robot will take in the future. So it's both planning ahead and optimizing the plan. Does that kind of is that clear?
And
I don't know.
so I think I'm getting it. I can't, well, so, but you did ask something about like shaking, right? You asked shaking because it's one of those things that it's hard to tell because it's kind of like a repeated action.
Yeah. That's why I was asking about it, was because like, so if it's shaking like this and he's always predicting, my thought there, what I was trying to understand with the shaking was like whether or not there are cases where this loss that he's proposing, where it goes always directly to the final position, would hurt it. And the final position, meaning again, it's not like the final position where the object's going to end up. It's a final position along this trajectory. But the point is that if I'm shaking, the thought here was that this was me trying to come up with a counterexample. So I'm not actually sure if this is correct. But the thought is that at each point, it's much more like it doesn't actually matter if I get the final position on the shaking right. It matters if I get the local kind of velocity right. And so maybe it doesn't help, right? Because I just want to get this mode. So I was trying to think if there were cases where it wouldn't, where this assumption that you want to regularize that straight line path through trajectory space, and like where that regularization would help or hurt. And I'm still not sure if I'm not still not sure. Like I think that all of his were these very kind of smooth trajectories, which don't have this
like
kind of,
there's a clear start and a clear end to the thing. Whereas shaking is like it's like a infinite.
It's not
in the loop.
Yeah, it's cyclic. It's also like like if something goes wrong and I don't really care if maybe if there's a small deviation, I shouldn't adjust for that by trying to force myself back onto the line later. I should do this little. So I'm not sure exactly. I need to think about that more. But yeah, but I mean, not that it matters. Most things that we want robots to do are to move precisely.
That's true.
So
yeah, it's start to end. Usually there's a start and an end.
Yeah.
Yeah, I mean, I also think like the aspect that he has this like multimodality consideration.
Yeah.
I don't comprehend it fully, but what I take away is that there's a way to basically more intelligently take in different modalities instead of just like attend to the right modalities, the right portion of time. Yeah. So I think that would be this kind of thing will be very useful because like I mean humans have multiple sense, right? Vision, sense of touch and whatnot, and so all these have to inform the actions. God knows what is going on in our brain, how much of text is going on. Right. For example, I don't know whether I point. Yeah, at the Coral at our booth, we have this like grandmaster of origami guy, right?
Yeah.
Doing origami. So I was observing him for like at least 10 minutes continuously, just to like on the side. He doesn't know I was watching him. Half the time I kid you not, he is not looking. He's just doing this.
He just
talking
knows
to
it all. He's got the,
it's like touch and then occasionally he'll glance it a little bit or just and then go. And yeah, so it's but yeah, in any case, like I think having this, we can't just always rely on vision alone. Like vision definitely, I mean occlusion, like even with 3D, right? I think 3D definitely helps.
Yeah.
Probably still not sufficient for some tasks,
Yeah.
like origami folding. But I mean, glad to see all this like very like I guess fundamental like improvement. Hopefully, because these things, if it does work, then everyone will get to use it and get the benefit.
Yeah, I think so.
It's like the whole thing. It's like could be even a small change and small improvement, but the whole field get to use it, and the impact could be like 1000x.
Right.
Yeah.
Well, okay. On the multimodality thing, I think there's something else that I should probably clarify because, like, most like Pi is also like, or like the Pi Zero. Most of these things are multimodal. Flow policies are all DIT is multimodal, but like the particular thing he was talking about is it's like a subtle technical detail. It's that like the embedding coming in, like so we're talking about how you're basically learning to optimize this trajectory and get all these points into the line that you're going to follow, right? So that model in the previous version in DIT, his baseline was conditioned on just like a single embedding, so like a single token.
Just append. So it's like it look like that like. There's no differentiation between the different modalities, is what you're saying.
No, but so there is like but it's all done beforehand and compressed down into a single token,
Yes.
right? So like that's the thing that he was changing. So he inserted this cross attention block, which means that now I add in just time and in my embedding condition, and then there's an attention back to everything. So then it can do something like it can pay attention to, well, is my understanding, right? Maybe more, but like then it can like pay attention to. It can say like if I'm like trying to refine the trajectory and like I'm trying to line them up around like maybe the picture frame that's behind me, then it can like when it's refining this point, it can like visually attend to this information here on the picture, and that'll help it get into the correct position, right? Whereas beforehand, it would have had to figure out how to squeeze all that information through this one embedding token, and so it's like again, it's a very technical thing. It's not like it couldn't do it before. It's like it can do it better now, and hopefully a lot better. And like but it's like at some point these kinds of like low level technical details are what's going to make the difference between these things working and not, because a lot of them don't work right now, right? So that's the and I think the other thing is that it should increase the capacity of the models to solve like really hard problems potentially. So we'll just have to see, right? That's
I think that's why you asked the question at that juncture, like about like wouldn't the model be quite big, and then but it turns out it's more efficient and therefore it's worth it. Yeah. I guess it's essentially, it strikes me that they basically maybe prior to his like work here, most guys just like don't even allow the model to attend to it. Like, the abstraction is done just at different level, right, between the different modalities. So presumably.
And so
cool.
So there's other architectures and stuff too, but yeah, it's a very it's a research paper.
Cool.
It's like a real academic conference paper.
Cool. Yeah. I think we should have this like guys come on every now and then, and hopefully you can ask all other questions. I can do the opening and closing. But actually that paper that he mentioned to us, and also sounds crazy. I think we should try to
We'll have to go.
All right, cool. All right. Till next time, Chris.
See you.
Ciao.